All right, this is our section 8.6 review. We're starting with a Taylor series. So I'm going to assume that we have some established background knowledge, and I'm just going to go through how I would solve some of these problems. So let's start with, that's not a good screenshot. Let's start with this one. So we're trying to find the Taylor series of 3 over 4 minus x. So we want it to look like this form. Right, this is our 1 over 1 minus r. So we want to make the denominator look like that. So I'm going to pull the numerator out. So it's going to be 3 times 1 over. I'm going to pull a 4 out. It's going to be 1 minus 1/4 x. So that whole thing is going to simplify down to that. And that looks like our 1 over 1 minus r formula. So I'm going to set this equal to 3 over 4 times the summation of n equals 0 to infinity of, this is going to be negative 1 to the n times x over 4 to the n. Oh, I lied. So I put a negative there. There's not supposed to be a negative. So this whole thing is actually just x over 4 to the n. Since the formula is in this form, if it's negative already, then that's fine. If you have something like 1 over 1 plus x, well, the coefficient in front of this, in terms of this equation, the coefficient is negative 1, because it's a minus a negative 1x, right? There'll be an example of that later. I just jumped the gun. So this is equal to 3 over 4. Yeah, 3 over 4. I'm going to break this into x to the n over 4 to the n. And then I'm just going to multiply our constant here. So this whole thing is going to simplify down to 3x to the n over 4 to the n plus 1. I said in a previous video, when you're multiplying two pieces that have the same base, what you do is you add the exponents. So this is equal to 4n plus 1. So this would be your answer. Next, let's do this one. Why does it always do that? Find the power series of the function x squared over 2 plus x. So I'm going to do the same thing here. I'm going to pull out an x over 2 to make our function look like it's supposed to. So this is going to be 1 plus x over 2. So now we can set up our summation. We have an x squared over 2 in the front, n equals 0 to infinity. So notice you have an addition sign here, so we're going to have to subtract. We're going to have a negative 1 term here. So I'm just going to pull that out so that I don't have to worry about it. I'm going to do x over 2 to the n. I mean, like, this is our answer, but we're going to simplify it, right? If we notice that this portion is x to the n over 2 to the n, now we can multiply our constants. So for the final answer, we're going to get n equals 0 to infinity. X to the n times x squared is x to the n plus 2. 2 to the n times 2, since they're both in the denominator, is going to be 2 to the n plus 1. And then don't forget we have that negative 1 to the n. So that is the answer for that one. Now let's look at one more like that, I suppose. So our function x cubed over 4 minus x, I'm going to pull out an x over 4, or x cubed over 4, and this is going to simplify down to 1 over 1 minus x to the x over 4. So now we can set up our summation here. We have x cubed over 4 times the summation from n equals 0 to infinity. We do not need a negative 1 term because this is already a negative. So it's going to be x to the n over 4 to the n. And it's going to follow the same principle as last time. We're going to multiply these and add the exponents. So this is going to be x to the n plus 3 over 4 to the n plus 1. Hopefully that's feeling pretty familiar and comfortable to you now. All right. Let's look at these ones. These ones are having you solve for the ln Taylor series. I would highly recommend just committing these to memory because otherwise they can be kind of annoying, right? So we're going to use this hint for ln 1 plus x. So 1 over 1 plus x. We know that that is equal to the summation as n equals 0 to infinity of negative 1 to the n, x to the n. So we want to integrate both sides so that the left side looks like ln 1 plus x, and the right side looks like this summation. So we're going to take the integral of this portion. And when we do that, we're going to get negative 1 to the n, right? And then x to the n plus 1 divided by n plus 1. This is just a simple integration technique, right? Add to the exponent, divide by the new power. So this is going to be our answer. You might see it written differently. There's a standard form of summation to index it. So this could be n plus 1 x to the n over n. So if you plug in 0 into here, it's going to be x to the 1 over 1. If you plug in 1 into here, it's going to be x to the 1 over 1. So these are equal. It's just for sake of simplifying this x value exponent. They standardize it like this. So that is the answer for that one. Let's erase. So now we're going to do ln 1 minus x. So if we think about what the power series for this one looks like, I'm just going to bring the negative out in front right now, and it's just this. So if we integrate both sides, we're we're going to get x to the n plus 1 over n for this term. There's a negative out in front. And if you'd like to, you could standardize it so that it's x to the n over n to infinity. So that is the answer for that one. This part is very important. Do not forget the negative sign. All right, and lastly, we're going to look at this final one. Again, this review is having you do these Taylor series by hand. I would highly recommend just committing these to memory because you're going to use them so often, and you're going to want to be able to recognize that. So this is having us find the power series of arctan. So first I'm going to identify that the derivative of arctan is this, and that represented as a power series is going to be -1 to the n, x squared to the n. So I'm going to rewrite that as x to the 2n. Now we're going to integrate both sides. So we get arctan on one side, and this is equal to n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. So that is all for the section 8.6 review. Thank you very much.